Table show the properties of steel used for the rotor. The most important number, the yield strength at 250 megapascal. This is the maximum stress the steel can take before it bend permanently. We'll also use Young modulus of 200 gigapascal, which they tell us the material very stiff and strong. Since the simulation only reached about 3 megapascal, we will below the failure limits, means the design is perfectly safe. The Y material summary. Yield strength 2.5 multiply 10 power of 8 the material breaking point. Young modulus 2 times 10 power of 11 how much the steel resists stretching. Density 7890 the weight of the steel, and the lastly thermal expansion 1.17 multiply 10 power of -5 how much it expands when it gets hot. Now we looking the ventilate this simulation. You will immediately notice a more complex stress pattern caused by internal cooling vents. While the peak stress in the first frame reached 3.11 megapascal due the pad's initial contact, the subsequent stage have a very efficiency distribution, average around 1.29 to 1.51 megapascal. Notice the rebate appearance of the stress rings. This correspond to the initial structure of the vent, although the peak stress is slightly higher than the solid disc. This design is superior for thermal management preventing long-term break fat as structure webbing under high heat condition. Overall, the design remained well within safe operation limits.
So as we all know, there are two types of disc brake rotors in this experiment, which are the solid disc brake rotor and the ventilated disc brake rotor. And for each type of disc brake rotor, we have two cases, which are the static case and frequency case. Table 2 shows the assigned material properties of solid disc brake rotor for static case. And for each case, we applied three different values of load, which are 2346 Newton, 1000 Newton, and 500 Newton. In table 2, for a load of 2346 Newton, the maximum von Mises stress is found to be 9.84 times 10 to the power of 5 Newton meter squared. And the minimum von Mises stress is 1.44 times 10 to the power of 5 Newton meter squared. Translational displacement, we have found it to be 0.000458 millimeter. For the second value of load, the maximum stress value is 9.79 times 10 to the power of 5 Newton meter squared, while the minimum value is 1.52 times 10 to the power of 5 Newton meter squared. For the third applied load, 500 newtons, the maximum stress is 9.94 times 10 to the power of 5, while the minimum is 1.64 times 10 to the power of 5. For table 3 shows the assigned material properties of solid disc brake rotor for frequency case. So for the first applied load, the maximum von Mises stress is found to be 7.33 times 10 to the power of 11, whereas the minimum von Mises stress is 1.13 times 10 to the power of 10 Newton meter squared, and the translational displacement is 530 millimeter. When the applied load has a value of 1000 newtons, the maximum von Mises stress is 7.26 times 10 to the power of 11, while the minimum von Mises stress value is 1.04 times 10 to the power of 10. When the load is 500 newtons, the maximum von Mises stress is 7.26 times 10 to the power of 11 Newton meter squared, and the minimum von Mises stress is 1.06 times 10 to the power of 10 Newton meter squared. Tables 4 and 5 show the assigned material properties of ventilated disc brake rotor for static and frequency case. For table 4, which is the static case, with the first applied load value of 2346 newtons, the maximum von Mises stress value is 9.96 times 10 to the power of 6 Newton meter squared. The minimum von Mises stress value is found to be 2.24 times 10 to the power of 5 Newton meter squared. And the translational displacement is 0.000478 millimeters. For the second applied load, the maximum von Mises stress is 1.15 times 10 to the power of 6 Newton meters squared, while the minimum von Mises stress is 1.86 times 10 to the power of 5 Newton meters squared. For the third applied load, the maximum value is 1.03 times 10 to the power of 6 Newton meters squared, whereas the minimum value is 1.75 times 10 to the power of 5 Newton meters squared. Table 5 shows the stress values and translational displacement value for the frequency case. So for the first applied load, the maximum von Mises stress value is 9.44 times 10 to the power of 11 Newton meters squared. The minimum von Mises stress value is 2.77 times 10 to the power of 10 Newton meters squared. And the translational displacement is 711 millimeters. For the second applied load, with a value of 1000 Newton, the maximum von Mises stress value is 9.36 times 10 to the power of 11 Newton meters squared, while the minimum von Mises stress value is 2.88 times 10 to the power of 10 Newton meters squared. For the third applied load, the maximum von Mises stress is 9.31 times 10 to the power of 11 while the minimum von Mises stress value is 2.69 times 10 to the power of 10 Newton meter squared.
Moving to the numerical results, we calculated the safety factor by dividing the yield strength by the von Mises stress. Looking at the comparison table, at a maximum load of 2,346 Newton, the solid disc maintained a high safety factor of 254.07, while the ventilated disc dropped significantly to 25.10. As the load decreased to 1000 Newton and 500 Newton, the safety factor for the solid disc remained relatively stable, calculated at 255.36 and 251.51 respectively. For the ventilated disc, the safety factor improved as the load decreased, rising to 217.39 at 1000 Newton and 242.72 at 500 Newton. In all tested scenarios, the solid disc provided a higher safety factor, indicating it remains further from the material yield point under these specific conditions. Now, let's discuss our findings. To begin, we use von Mises stress, a scalar value derived from the stress tensor to predict yielding in our ductile materials under loading. Based on this, we calculated the safety factor. In this experiment, that is the ratio of the material's yield strength to the observed von Mises stress. Regarding the hardware, a solid brake disc is a single thick unit without internal air channels. Because it lacks these channels, it suffers from poorer cooling. Consequently, the solid disc exhibits higher von Mises stress than a ventilated disc due to thermal expansion and uneven heat distribution during braking. Ultimately, because the stress in the solid disc approaches the material yield strength.
For discussion, a ventilated disc brake has two parallel plates with internal vent for airflow, providing better cooling from the lower thermal stress. A ventilated disc brake should have a lower von Mises stress because the temperature gradients are reduced. The safety factor is higher due to the reduced stress. A solid brake disc performance in heavy braking is prone to fade, whereas a ventilated brake disc provided better resistance. In conclusion, both the solid and ventilated brake discs are considered to be safe ventilated by the value of the safety factor, which is above 1. The results show that the von Mises stress for a solid case is lower compared to a frequency case. This shows that a brake disc rotor made with steel will not deform easily under high load, but thermal stress resistance varies among the structure of the brake disc. That's all from our group. Thank you.